Hello and welcome to Grace tutorial. In this video lecture, we will be discussing about the part 7 of aldehydes, ketones and carboxylic acids. Well, in the previous lecture, we had discussed about the different reductions of aldehydes, ketones and aldehydes as well as the ketones. That means the aldehydes and the ketones have been reduced into the various forms. Well, in part 6 of the video lecture, the reduction to alcohols have been explained in a very detailed and systematic manner. That is, so in the previous lecture, we had discussed about the reduction to alcohols. That means when the aldehydes and ketones are reduced in these methods, in these various methods, then alcohols are obtained. Well, we have the catalytic reduction with complex metal hydrides like the lithium aluminum hydride, and Marvin-Poundorf reduction, along with the reduction with sodium or alcohol. So all these are the methods in which the aldehydes and ketones are reduced to form the alcohols. Let us look at some other reductions. When the aldehydes and ketones are reduced, in some cases there may be a probability or there may be a chance of forming the alkanes. So that's what now we'll discuss, the reduction to alkanes. That means when the aldehydes and ketones are reduced to that it will be reduced to alkanes. Let me give you one simple example. We have the method that is Clemmensen's reduction. Clemmensen's reduction. So what is this Clemmensen's reduction? Clemmensen's reductions, and the alkanes are obtained from aldehydes as well as the ketones, no doubt. But if the question is asked that what do you mean by the Clemmensen reduction, we need to say that when aldehydes and ketones are reduced with a mixture of zinc amalgam. Suppose I have acetaldehyde, CH3CHO. Reduction, addition of hydrogen, zinc amalgam means Zn or Hg, and concentrated HCl. So this is basically called the zinc amalgam. That means this is aldehyde, this is the group of aldehyde, that is acetaldehyde. And when this acetaldehyde is reduced with the mixture of zinc amalgam, that is zinc or mercury and concentrated HCl, then what is basically obtained here? We get, that is ethane is obtained. That means, this acetaldehyde has been reduced to form ethane, and this is what called the Clemmensen's reduction. If we will take acetone, what happens? Let us take the acetone. So what is the formula for acetone? CH3CO CH3. So this is the formula for acetone. Similarly, when it is reduced with zinc amalgam and concentrated HCl, then it gives this is called propane. Yeah. And here this is acetone. That means what we need to understand from this Clemmensen reduction, all these are the different methods, all these are the reduction to alcohols. That means using all these methods, the alcohols are obtained from aldehydes and ketones. On the other hand, if the reduction takes place to the aldehydes as well as the ketones, there are some cases in which the alkanes are obtained. So the first method that we prepare the alkane by reducing the aldehyde as well as the ketone is that the Clemmensen's reduction. Clemmensen's reduction is very simple to understand and it's very relevant for the examination point of view. When the acetaldehyde gets reduced means what? Addition of hydrogen or the removal of oxygen. So when acetaldehyde gets reduced in the presence of zinc amalgam, that is zinc or Hg, and concentrated HCl, then alkane, that means ethane, is obtained. Similarly, when acetone gets reduced in the presence of zinc amalgam, then propane results. So this is what the alkanes are obtained here. So this is what called the Clemmensen's reduction. Now we have another type of the reduction wherein the alkanes are obtained, that is Wolff-Kishner reduction. So if we look at the Wolff-Kishner reduction, here also the alkanes are obtained, but this is something different. You just follow me. Suppose I have aldehyde. So this is the formula for aldehyde, RCHO. If I will treat this aldehyde with H2N NH2. So what is the formula for H2 and NH2? This is hydrogen. We had already done this reaction with the elimination with water molecules. Here in this case what happened? The H2 and O, the water is eliminated. But here we need to put the agent, that is KOH or glycol. That means when the aldehyde reacts with hydrogen in the presence of the potassium hydroxide in glycol, then first of all we'll get NNH2. So this is aldehyde hydrazone. Aldehyde hydrazone. If you will treat this again with KOH or glycol, then you will get alkane. Plus nitrogen. Let us take the specific example so that you can understand it well. Putting CH3 here, H2N NH2 in the presence of KOH or a glycol. First of all, water is eliminated from here. NNH2. So since we have taken acetaldehyde, this is acetaldehyde hydrazone. Acetaldehyde hydrazone. When it is again treated with KOH or glycol, then what happens? When it is again treated with KOH or glycol, then ethane is obtained with the liberation of the nitrogen gas. But if you will take acetone, CH3, C double bond O, this is acetone. If you will react with H2 and NH2, the water is eliminated from here and it gives acetone hydrazone. If it is again treated with KOH or glycol, then alkane results, but that alkane is propane along with the liberation of the nitrogen gas. This is acetone. When the acetone reacted with hydrogen in the presence of KOH or glycol, first of all the water has been eliminated from here. Then the remaining substances that we have put, that is acetone hydrazone. When it is again, if it is further treated with KOH, that means potassium hydroxide and glycol, then it gives propane. And finally nitrogen gas is obtained. So what did we understand here? Both are the reductions to alkanes. You may take the Clemmensen's reductions or Wolff-Kishner reductions. What is the main objective of this reduction? The formation of alkane. That means aldehydes and ketones can be reduced to form the alkane, and this is proved by both the Wolff-Kishner reductions as well as the Clemmensen's reductions. Well, this is all about the reduction to alcohols as well as the reduction to alkanes, by the aldehydes as well as the ketones. Now we'll look at one of the most important chemical reaction, which is very, very important for your examination point, that is aldol condensation. So if we look at this chemical reaction, aldol condensation, first of all we need to understand that what do you mean by the aldol condensation. When a mixture of aldehydes and ketones react together in the presence of dilute alkali, it may be the sodium hydroxide or the barium hydroxide, that means the dilute NaOH or dilute BaOH2, then the product which is obtained is beta hydroxyaldehydes or the beta hydroxy ketones. The product which is obtained, it contains both the aldehyde as well as the alcohol group. That's why this reaction is also known as the aldol condensation. So aldol, that means the compound, it consists of both the aldehyde as well as the alcohol. Let me repeat what do you mean by aldol condensation once more. When a mixture of the aldehydes and the ketones react together, and that is also having at least one alpha hydrogen atom. At least one alpha hydrogen atom is very much important in the aldol condensation. That means the aldol condensation takes place in that compound only if it is having at least one alpha hydrogen atom. So what do you mean by this alpha hydrogen atom? The hydrogen atom which is connected to the alpha carbon, that carbon is known as alpha hydrogen atom. So let me give you a clear idea. Suppose I have CH3, CHO. If you look at here, I have written acetaldehyde. So what is the functional group here? CHO is the functional group. Aldehyde group, functional group is attached to that. So in this functional group, the carbon which is attached, that carbon is known as alpha carbon. And these three hydrogens are attached in the surrounding way to this alpha carbon. That's why these hydrogens are known as alpha hydrogen. So what is alpha hydrogen? The hydrogen which is attached to the alpha carbon. Those hydrogens are called the alpha hydrogens. So in this aldol condensation, the aldol condensation takes place in that chemical reactions in the mixture of the aldehydes and ketones in the presence of the dilute alkali, that is dilute NaOH or the BaOH2, and that's also having at least one alpha hydrogen atom. That you must remember this in aldol condensation. In aldol condensation, at least one alpha hydrogen atom is required, because without having the alpha hydrogen atom, the aldol condensation does not take place. So the product which is obtained here, those products are either the beta hydroxyaldehyde or the beta hydroxy ketone. Since the product consists of both the aldehydes as well as the alcohol, that's why this reaction is called the Aldol Condensation. So I hope you understood what do you mean by the Aldol Condensation. Let me give you the example. I have acetaldehyde, CH3CHO, right? If you look at here this acetaldehyde, basically this is the carbonyl group. I had already explained you in the previous lecture about the structure of the carbonyl group, wherein we had discussed in the carbonyl group, here oxygen is basically an since it is having the highly electronegative, that's why it attracts, it attracts the shared pair of the electron towards itself. As a result, there is a slightly negative charge is formed. Similarly, a slight positive charge is formed here in the carbon. Similarly, if you look at here, a slight positive charge is obtained and here a slight negative charge is obtained. So what happens here basically, when a mixture of these aldehydes, both of the compounds are acetaldehydes, but I have written here slightly different. Why? Because you see CH3CHO, this is acetaldehyde. This is also CH3CHO. That means here hydrogen atom is there. I have just split. That means I have just separated, divided this CH3. H bond CH2. That means this is CH3. CH3 and this is CHO. That means both the compounds are acetaldehyde. So a mixture of acetaldehydes have been taken in the presence of dilute alkali. So what happened here? The hydrogen atom, which is partially positive charge, that will be attracted by the oxygen atom, which is partially negatively charged one. And finally here it is obtained CH3CH. CH3CH, and this partially, the partially negatively charged oxygen atom attracts the partially positive charged hydrogen atom, and it finally gives OH. And what we have remaining, CH2CHO, that's what we have written, and this is what called acetaldehyde aldol. But now we need to understand that how the product is obtained. In order to understand the formation of the product, let us try to understand the mechanism of the aldol condensation, which plays a very crucial, significant role in this reaction. First of all, we have taken acetaldehyde. If you look at here in this acetaldehyde, this is partially negative charge and this is partially positive charge. When it reacts with the alkali, the OH minus, what happens here, since it is partially negatively charged, that means the shared pair of the electron will be attracted more towards oxygen atom. So that's one of the point. But here we need to understand something slightly different. The hydrogen atom is there in the beginning. This hydrogen atom, since it is positively charged one, it reacts with the negatively charged one, that is OH minus, and it gives H2O. So what happens here, the shared pair of the electron is slightly attracted by the carbon atom and it forms the negative charge here. So this is a nucleophile. That means a nucleophile is formed in the first step of the mechanism. So it's very simple to understand the first step of the mechanism. We have acetaldehyde. When the acetaldehyde reacts with the OH minus or alkali, the positively charged hydrogen atom reacts with the negatively charged hydroxide ion to form the water. So finally what we have, the shared pair of the electron will be attracted towards the carbon atom, and it finally produces the C minus. That means a nucleophile is obtained. So what is this nucleophile? The nucleophile is one of the most reactive intermediate. Nucleophile means the nucleus loving species, or we can say the electron rich species. So a nucleophile is obtained. In the next step, what happens here, the nucleophile which is obtained, that nucleophile reacts with acetaldehyde again once more. Why? Because here we have taken the mixture of acetaldehyde. So when this nucleophile reacts with this acetaldehyde, here basically what happened, the shared pair of the electrons here will be attracted more towards the oxygen atom, since it is highly electronegative. Because of the region the oxygen is highly electronegative than that of the carbon atom, the shared pair of the electron, this shared pair of the electron will be attracted by the oxygen atom towards itself. As a result, finally it gives the O minus. So CH3C. So and here it is single bond and O minus is obtained. O minus, and we have CH2CHO. CH2CHO. This is what here it is obtained. And now what we will do, look at here, I have CH3, CH, this is O minus, CH2, CHO. Here this is the product obtained. If I will react it with water, if you will dissociate with water, what do you get? If you will dissociate with water, you will get H plus and OH minus, right? So this H plus now reacts with, it will be attracted by the oxygen atom, which is electron negative. So what happens here finally? CH3, CH, single bond CH, now here it is OH, and CH2, CHO. And finally OH minus is obtained. And this is what the main product that we need to understand. So this is the mechanism. Finally, I think the product is obtained, that is acetaldehyde aldol. So this is what the acetaldehyde aldol. That means a mixture of the aldehydes as well as the ketones react together, having at least one alpha hydrogen atom in the presence of the dilute alkali such as sodium hydroxide or the barium hydroxide. The products which is obtained are known as the beta hydroxyaldehydes or the beta hydroxyketone. Since the products contains both the aldehyde as well as the alcohol group, that's why this reaction is called Aldol condensation. Let me react with CH3, CHO. Again, CH3, CHO. Both the compounds are acetaldehydes. Here what happened? CH3, CH, this OH, it comes here, and we have CH2, CHO. So what is the name of this compound? And here we need to mention dilute NaOH, or we can say barium hydroxide. So what is the name of this compound? The name of this compound is 1, 2, 3. That means 3 hydroxy, 1, 2, 3, 4. 4 carbons are there. So 3 hydroxy butanol. 3 hydroxy butanol. Similarly, if I will react the acetone, CH3, CO, CH3, then HCH2, CO, CH3, both are acetones. If I will react together in the presence of the dilute NaOH with the barium hydroxide, here what happens basically? The OH, that means CH3, CH, CH3, CH3, OH, CH2, CO, CH3, CH2, CO, CH3. So this is what here it is obtained. So what is the name of this compound? The name of this compound is 1, 2, 3 and 4. That means the 4 hydroxy 4 methyl. 4 hydroxy 4 methyl, 1, 2, 3, 4, 5. 4 hydroxy 4 methyl pentanone. 4 hydroxy 4 methyl pentanone. Here we need to write 4 hydroxy 4 methyl pentanone. Because it is ketone group is there. I have just done nothing but CH3 is there and CH3 I have just placed here, and one carbon is there, carbon, and this O, it reacts with OH, and finally CH2, CO, CH3, this is what. So 4 hydroxy 4 methyl pentanone. 4 hydroxy, in the 4th position hydroxy group is attached to 4 hydroxy, and in the 4th position as well methyl group is also attached to 4 hydroxy 4 methyl. How many carbon atoms are there? 1, 2, 3, 4, 5. Since the 5 carbon atoms are there, that's why the name 4 hydroxy 4 methyl pentanone. But what the aldol condensation here that I have done, this is what called the simple aldol. These aldols are simple aldol. So what do you mean by the cross aldol? let me analyze the point of the cross aldol. In cross aldol, what do? Suppose you have acetaldehyde, CH3 CHO. Now if it reacts with acetone in the presence of dilute NaOH or BaOH2, barium hydroxide, look at here. Here the compounds are different, means the one acetaldehyde has been taken, another acetone has been taken. Now what happens? CH3 single bond CH, CH3 single bond CH, here OH. Why? Because this O and H, again CH2, again CO, CH3. What is the name of this compound? 1, 2, 3, 4. So 4-hydroxy, 4-hydroxy 1, 2, 3, 4, 5. 4-hydroxy pentanone. 4-hydroxy pentanone is obtained. Similarly, if I will take first of all CH3 CO CH3, HCH2 CHO, that is acetaldehyde and acetone, in the presence of the dilute alkali or the sodium barium hydroxide, what happens? CH3 here, CH3 C, CH3 CH3 and here OH, CH2 CHO. So look at here, the 1, 2, 3. So 3-hydroxy 3-methyl, 3-hydroxy 3-methyl, 1, 2, 3, 4. Since aldehyde group is attached, so 1, 2, 3, 4, that is butanol. So 3-hydroxy 3-methyl butanol is obtained. This is acetone and this is acetaldehyde. Yeah. And what the two examples that I have shown for you, these are called the crossed aldol. Crossed aldol. So what's the difference between the simple aldol and crossed aldol? Here you need to mention, when a mixture of the two same compounds gets condensation in the presence of the dilute alkali like sodium hydroxide or the barium hydroxide having at least one alpha hydrogen atom, then the compounds which are obtained, those compounds are beta hydroxy aldehydes or beta hydroxy ketones, no doubt. But when the different compounds are taken, then that is called the crossed aldol. But when the same compounds are taken, when a mixture of same compounds are taken, that is called simple aldol, which I have just shown here. When different compounds are taken, those are called the crossed aldol. So what is this aldol condensation reactions means? What do you say that? When a mixture of the carbonyl compounds like the aldehydes as well as the ketones having at least one alpha hydrogen atom react together in the presence of the dilute alkali like the sodium hydroxide or the barium hydroxide, then the product which is obtained is known as the beta hydroxy aldehydes as well as the beta hydroxy ketone. So the product which contains both the aldehyde as well as the alcohol group, that's why these products are also known as the aldol condensation. And here in the aldol condensation, the simple aldol condensation takes place if the mixture of the same groups, if the mixture of the same compounds have been taken. The condensation is said to be crossed aldol if the different compounds have been taken and mixed in order to form the aldol condensation. That is called the crossed aldol condensation. So here we have discussed the aldol condensation in a very detailed and the systematic manner along with the mechanism, with the specific examples and the differences between the crossed aldol as well as the simple aldol, the naming of these compounds. I hope the aldol condensation is very clear for you, because this is very much relevant for the examination point, which is very often comes every year. Explain aldol condensation, right? When a mixture of the carbonyl compounds react with a dilute alkali, then the products which is obtained, name the products, or explain the mechanism of the aldol condensation. In this way, we need to remember each and every bit regarding to the aldol condensation, along with the reaction with the specific examples as well. Well, this is what we have completed the aldol condensation, and in this session one of the most other important reaction is there. That's what called the Kennedyros reaction. Now we will discuss the Kennedyros reaction.